Now question number 6 is x dy minus y dx is equal to under root x square plus y square dx. So x dy, transposing this term to right hand side, we have under root x square plus y square dx plus y dx. X dy is equal to, taking dx operator common out of these two terms, we have inside the bracket under root x square plus y square plus y dx. Now transposing dx to left hand side and x to right hand side, we have dy upon dx is equal to bracket under root x square plus y square plus y upon x. Let it be equation number 1. Now let y is equal to ux. Let it be equation number 2. Differentiating with respect to x, we get dy upon dx is equal to u plus x du upon dx, be equation number 3. From equation 1, 2 and 3. Replacing dy upon dx by this expression u plus x du upon dx in equation number 1, we have on the left hand side u plus x du upon dx, and on the right hand side, replacing y by ux in this expression, we have under root x square plus u square x square plus x plus ux divided by x. So u plus x du upon dx as it is. Here we may take x square common out of root, it becomes x outside. Under root we have 1 plus u square only inside the root plus ux divided by x. Now u plus x du upon dx, taking x common out of these two terms, this x will cancel this x. So we have only under root 1 plus u square plus u on the right hand side. And as you see, this u will cancel this u because on transposing this u we get minus u over here, so plus u minus u will be cancelled. Now we are left with x du upon dx on the left and under root u 1 plus u square on the right hand side. So transposing under root 1 plus u square to left hand side and x dx to right hand side, we get 1 upon under root 1 plus u square du is equal to 1 over x dx. Now integrating both sides, we get integral 1 upon under root 1 plus u square du is equal to integral 1 upon x dx. So using identity, integral 1 over under root a square plus x square dx is equal to log mod x plus under root a square plus x square. We may integrate this term as log mod u plus under root 1 plus u square, and on the right hand side there is 1 over x dx, so its integral will be log mod x plus constant of integration should also be taken as log c. So now since from equation number 2 we had assumed y is equal to ux, so from this u is equal to y upon x. So replacing u by y upon x in this expression, we have log y upon x plus under root 1 plus y square upon x square is equal to log mod x plus log c. Now taking LCM. Now y over x and taking LCM over here inside the root, we have under root x square plus y square upon x square is equal to log mod x plus log c. Now log, this may be written as y upon x plus under root x square plus y square upon x, because under root x square is x, so that is log mod x plus log c. Taking LCM over here, we have y plus under root x square plus y square in the numerator and x in the denominator. That is equal to log mod x plus log c. Using the property log m upon n as log m minus log n, we may write it as log modulus y plus under root x square plus y square minus log mod x is equal to log mod x plus log c. Transposing log mod x to right hand side, we have log mod y plus under root x square plus y square. And on transposing log mod x to right hand side, it becomes positive and will be added to this term. So that will become twice log mod x plus log c. Now proceeding from this step, on the left hand side, as we have log y plus under root x square plus y square is equal to. This 2 may be taken to the power of, may be written as log x square plus log c. So log mod y plus under root x square plus y square is equal to, using the logarithmic property log m plus log n is equal to log m into n, we may write it as log cx square. Now eliminating log from both sides, we have y plus under root x square plus y square is equal to cx square, and this is the required solution of the given differential equation. Now question number 7 is x cos y upon x plus y sin y upon x bracket close y dx is equal to bracket y sin y upon x minus x cos y upon x bracket close x dy. So first we need to find out the value of dy upon dx in terms of x and y. So transposing this dx to right hand side in the denominator of dy, and this whole expression to left hand side, which goes in the denominator of this expression. So we have curly bracket x cos y upon x plus y sin y upon x bracket close y divided by curly bracket y sin y upon x minus x cos y upon x curly bracket close x is equal to dy upon dx, which may also be written as dy upon dx is equal to. Out of these two terms, we may take x common. So we have x curly bracket cos y upon x plus y upon x sin y upon x bracket close y divided by, similarly we should take x common out of these two terms in the denominator. So we have x, now both the terms will be divided by x. So we get first term as y upon x sin y upon x minus cos y upon x bracket close, and there was x outside, so that is as it is. This x is cancelled by this x. So let it be equation number 1, and we have to assume let y upon x as u, or we may write it as y is equal to ux. Differentiating with respect to x, we get dy upon dx is equal to u plus x du upon dx, equation number 3. Now replacing dy upon dx by u plus x du upon dx in equation number 1. So we have u plus x du upon dx is equal to, on the right hand side we get cos u, because y upon x we had taken as u. So cos u plus y upon x becomes u sin u bracket close divided by, here in the denominator y upon x becomes u sin u minus cos u, and as we have outside these two brackets y in the numerator and x in denominator, so it is also y upon x, so it becomes u. Now proceeding from this step, transposing u to right hand side, we get x du upon dx on the left hand side, and on the right hand side we have cos u plus u sin u upon u sin u minus cos u into u and minus u. This u becomes minus u over there, so we have this expression. So here on the right hand side we have to take this bracket as LCM. So we have u sin u minus cos u. In the numerator, we have bracket cos u plus u sin u into u minus this bracket will multiply this u, so u bracket u sin u minus cos u. Now taking u common out of these two terms, there is u and there is also u. So taking u common, inside the bracket we have cos u plus u sin u, and here minus, this minus will change both the signs inside. So minus u sin u and plus cos u divided by u sin u minus cos u. As you see, u sin u positive and u sin u negative will be cancelled with each other. So we are left with u, and cos u plus cos u becomes 2 cos u divided by u sin u minus cos u. Now on the left hand side we have x du upon dx, and on the right hand side we have 2u cos u upon u sin u minus cos u. Now transposing this expression to left hand side and x dx to right hand side, we have u sin u minus cos u in the numerator and 2u cos u in denominator. Du is equal to 1 upon x dx. If we split them up, we have 1 upon 2 tan u, because if we divide u sin u by 2u cos u, u will be cancelled by u and sin u upon cos u becomes tan u, and 1 upon 2 as it is, minus 1 upon 2, and cos u will be cancelled by cos u. If we divide the second term by 2u cos u, only 1 upon 2, 1 upon u is left. Du is equal to 1 over x dx. So multiplying both sides by 2, we get tan u minus 1 over u. Du is equal to 2, 1 over x dx. Integrating both sides, we have tan u du minus integral 1 over u du is equal to 2 integral 1 upon x dx. Now proceeding from this step, as we know well, integral of tan u is log sec u minus, and integral of 1 upon u is log u is equal to 2. Integral of 1 upon x dx becomes log x plus log c. Now these two terms, using logarithmic property, log m minus log n is equal to log m upon n, may be written as log cq upon u is equal to. Now this too may be written in the power of x using logarithmic property. So we have log x square plus log c. Now log cq upon u is equal to, here using property log m plus log n is equal to log m into n, we may write this expression as log c into x square. Now eliminating log from both sides, we have cq upon u is equal to cx square. As we know from equation number 2, y upon x is equal to u. So replacing u by y upon x in this expression, we have sec y upon x upon y upon x is equal to cx square. For transposing y upon x to right hand side, we may write it as sec y upon x is equal to y upon x into cx square. Now cancelling one part of x from the numerator from the x in the denominator. This x will cancel one part of x from the numerator. We have sec y over x is equal to cxy, and this is the required solution of the given differential equation. Now eighth sum is x dy upon dx minus y plus x sin y upon x is equal to 0, keeping x dy upon dx on the left. Transposing these two terms to right hand side, we have y positive and minus x sine y upon x. Transposing this x to right hand side, we have dy upon dx is equal to y minus x sine y upon x. So dy upon dx. This x will divide both the terms, so splitting these two terms apart, we may write them as y upon x. When this x will divide y, we get y upon x minus, when this x will divide the second term, x will be cancelled by x, and we have only sine y over x. Let it be equation number 1. And now let y upon x as u, or y is equal to ux, differentiating with respect to x, dy upon dx is equal to u plus x du upon dx, equation number 3. Equation 1, 2, and 3. If we replace dy upon dx by the expression u plus x du upon dx, because this is exactly equal to dy upon dx from equation number 3 here in this equation number 1, we have u plus x du upon dx is equal to, on the right hand side, y upon x is taken as u from equation number 2. So we have u minus sine y upon x u. So transposing this u to right hand side, we have x du upon dx is equal to u minus sine u minus u. This u positive and this u is negative. Both are cancelled with each other. From this step, we have x du upon dx is equal to minus sine u. Now transposing this expression to left hand side, we have minus 1 upon sine u du is equal to x dx. To right hand side, we have 1 over x dx. Now integrating both sides, we have minus 1 upon sine u du is equal to integral 1 over x dx. That is minus integral cosec u du is equal to integral 1 over x dx. So integral of cosec u will be minus log cosec u plus cot u is equal to integral of 1 over x with respect to x is log x plus constant of integration is taken as log c. So this minus into minus becomes plus, and we have log cosec u plus cot u is equal to, this may be written as log cx using log m plus log n is equal to log m into n. Now eliminating log from both sides, we have cosec u plus cot u is equal to cx. Now as from equation number 2, u is equal to y upon x, so replacing u by y upon x, we have cosec y upon x plus cot y upon x is equal to cx. Cosec may be written as 1 over sine, so 1 upon sine y upon x plus cot may be written as cos upon sine, so cos y upon x upon sine y upon x is equal to cx. Multiplying both sides of this equation by sine y upon x, we may write it as 1 plus cos y upon x is equal to cx sine y upon x, and this is the required solution of the given differential equation. Now ninth sum is y dx plus x log y upon x dy minus 2x dy is equal to 0. So transposing these two terms to right hand side, we have y dx is equal to, this term becomes positive and this term becomes negative on transposition, so we have 2x dy minus x log y upon x dy. Y dx is equal to, taking x dy common out of these two terms, inside the bracket we have 2 minus log y upon x dy common. Transposing this expression to left hand side and dx to right hand side, we have y upon 2 minus log y upon x is equal to dy upon dx. So we may write it as dy upon dx is equal to y upon x. This may be written as y upon x in the numerator upon 2 minus log y upon x. Let it be equation number 1. So let y is equal to ux or y upon x as u. Differentiating with respect to x, we get dy upon dx is equal to u plus x du upon dx. So replacing dy upon dx by u plus x du upon dx, with the help of this equation, we have u plus x du upon dx on the left hand side, and on the right hand side y upon x becomes u, because by this assumption y upon x is equal to u. So we get u upon 2 minus log u. Transposing this u to right hand side, we have x du upon dx on the left, and on the right hand side u upon 2 minus log u minus u. Now proceeding from this step, x du upon dx on the left hand side and on the right hand side, taking 2 minus log u as LCM, we have 2 minus log u in the denominator, and in the numerator we have u minus u into 2 minus log u. So x du upon dx is equal to u, opening the bracket, this minus u will multiply both the terms inside, so we have minus 2u plus u log u divided by 2 minus log u. Now x du upon dx is equal to, one u is positive and 2 u are negative, so minus u is left plus u log u upon 2 minus log u. Transposing this expression to left hand side and x dx to right hand side, we have 2 minus log u divided by u log u minus u du is equal to 1 upon x dx. 2 minus log u, and as u is common out of these two terms in the denominator, we should take u common. So inside the bracket we have log u minus 1 into u du is equal to 1 upon x dx. Now integrating both sides, we have integral 2 minus log u divided by log u minus 1 into u du is equal to integral 1 upon x dx. Now here on left hand side, we need to assume log u as v, say, and differentiating, we have 1 upon u du is equal to dv. So let it be equation number 4. Now proceeding from this step, now left hand side of this equation becomes integral 2 minus v upon v minus 1 dv is equal to integral 1 over x dx. Now taking minus common out of it, we may write it as minus integral v minus 2 upon v minus 1 dv is equal to integral 1 over x dx minus integral v minus 2 may be written as v minus 1 divided by v minus 1 dv is equal to integral 1 over x dx minus integral v minus 1 upon v minus 1 becomes 1 dv, and minus into minus becomes plus integral 1 upon v minus 1 dv is equal to integral 1 over x dx. Integral of 1 with respect to v becomes v, so minus v, plus integral of 1 upon v minus 1 becomes log v minus 1 is equal to integral of 1 over x is log x and plus log c. This v should be transposed to right hand side, and these two terms to left hand side we have log v minus 1 minus log x minus log c is equal to v. Now as we know, v is equal to log u, so putting v is equal to log u over here, we have log bracket log u minus 1 minus, taking minus common out of these two, we have inside the bracket log x plus log c, which may be written as log cx is equal to v. This v may also be written as log u. So log modulus log u minus 1 is equal to, transposing this term again to right hand side, we have log u plus log cx. Using log m plus log n property, we may write this expression as log modulus log u minus 1 is equal to log c into ux. Eliminating these two log from both sides, we have log u minus 1 is equal to c ux. Proceeding from this step, u is equal to y upon x. So replacing u by y upon x, in this equation we have log y upon x minus 1 is equal to c y upon x into x. These two x are cancelled with each other, and ultimately we have log y upon x minus 1 is equal to cy. This is the required solution of the given differential equation. Now sum 10 is, now 10th sum is 1 plus e raised to the power x upon y dx plus e raised to the power x upon y bracket 1 minus x upon y dy is equal to 0. So first we have to transpose the second term to right hand side. So we have 1 plus e raised to the power x upon y dx is equal to minus e raised to the power x upon y bracket 1 minus x upon y dy. Taking minus common out of this bracket, this minus becomes plus, and we may write it as 1 plus e raised to the power x upon y dx is equal to e raised to the power x upon y minus 1 dy. Now transposing dy to this side and 1 plus e raised to power x upon y to the right hand side. So we get dx upon dy is equal to e raised to the power x upon y minus 1 divided by 1 plus e raised to the power x upon y. Let it be equation number 1. Let it be equation number 1. Now this is the second format of homogeneous differential equation where all the terms can be expressed as x upon y. So here the substitution is made as x is equal to uy. Not y is equal to ux, but x is equal to uy. Let it be equation number 2. And we have to differentiate it with respect to y. So on the left hand side we have dx upon dy, and on the right hand side first function as it is, the derivative of y with respect to y becomes 1, and plus y as it is, derivative of u with respect to y, du upon dy. Let it be equation number 3. So from equation 1, 2 and 3 we may replace dx upon dy by this expression using equation number 3 here in equation number 1. So we have u plus y du upon dy, and on the right hand side e raised to the power u, because if x is equal to uy then u will be x upon y. So it becomes e raised to the power u minus 1 upon 1 plus e raised to the power u. Now transposing this u to right hand side, we get y du upon dy is equal to e raised to the power u minus 1 divided by 1 plus e raised to the power u minus u. Taking LCM, 1 plus e raised to the power u. In the numerator we have e raised to the power u minus 1 minus u into 1 plus e raised to the power u. So proceeding from this step, on the left hand side we have y du upon dy, and on the right hand side, opening this bracket, we have u e raised to the power u, first term, and second term will be minus e raised to the power u, and here opening this bracket, this u minus u will multiply both the terms, and we have minus u e raised to the power u divided by 1 plus e raised to the power u. Clearly this term and this term are identical and having opposite sign. This is positive, this is negative, so these are cancelled with each other, and y du upon dy is equal to, and here we may take minus common out of these two terms, so we may write it as e raised to the power u plus u, and 1 plus e raised to the power u may be written as e raised to the power u plus 1. Now transposing this expression of u to left hand side and y dy to right hand side, we get e raised to the power u plus 1 upon e raised to the power u plus u du is equal to minus 1 upon y dy. So transposing y dy to right hand side, this y goes in denominator and this dy goes in numerator. So obviously this is variable separable form, so integrating both sides. Integral e raised to the power u plus 1 upon e raised to the power u plus u du is equal to minus integral 1 over y dy. Here we have to assume e raised to the power u plus u as t and differentiating with respect to t. We get e raised to the power u, and differential is e raised to the power u, and differential of u is 1 du upon dt is equal to differential of t with respect to t is 1. Transposing t to this side, we have e raised to the power u plus 1 du is equal to dt. So replacing e raised to the power u plus u by t, we get e raised to the power u plus 1 du is equal to dt. So our equation becomes 1 upon t dt is equal to minus integral 1 upon y dy. So on the left hand side we get log t, and on the right hand side minus log y. Now constant of integration should also be taken as log c. Now since t was taken as e raised to the power u plus u, so replacing t by e raised to the power u plus u, we get log e raised to the power u plus u, and transposing this term to left hand side, it becomes plus log y is equal to log c. Using log m plus log n is equal to log m into n, we may write it as log y e raised to the power u plus u is equal to log c. Eliminating log from both sides, we get y e raised to the power u plus u is equal to c. Now since from equation number 2 x upon y is equal to u, so replacing u by x upon y, we get y bracket e raised to the power x upon y plus x upon y is equal to c. Y, taking LCM inside the bracket y, we get y e raised to the power x upon y plus x is equal to c. This y is cancelled by this y, and finally we get y e raised to the power x upon y plus x is equal to c. And this is required solution of the differential equation.